Okay, so we're going to pause the video here and give you about 5 to 8 minutes to work on this warm-up before we unpause and you can see me do the answers. So if I'm going to make a sketch of the data, it says the highest temperature is 78.5 and the lowest is 43.5. And in month 0, we're at the low. In month 6, we're at the high. So that means 6 months later again, we're at the low. So if I connect my points, oh, I missed. That's right, you get the idea. That's a minimum. So if I want the amplitude, that's going to be our maximum minus the minimum divided by 2, which is 17.5. You could leave it as a fraction of 35 over 2 as well, doesn't matter. Our midline is if we add our maximum and minimum and divide by 2, which is 61. Our period is 12. And so now to write a sine and cosine function, I'm going to start with cosine. So we get 17.5 cosine. Our horizontal dilation value is 2 pi over the period. We can reduce that. My horizontal translation is to the right 6, and my midline is up 61. So if I simplify that, our horizontal dilation is pi over 6. So now for the sine sine function, I need to find out where the midline happens. So that's going to be here at 3. So my sine function is going to be moved to the right 3 and up 61. Okay, so this is page 39 in your packet. And please take a minute to answer number 1. So if this is on a coordinate plane, we have x and y. Let me make this bigger. There we go. So tangent of our angle is y over x. Does this change if the angle of rotation is in a unit circle, meaning the radius is 1? No. The ratio y over x won't change if r changes. Because remember, unit circle is a radius of 1. Okay, so now for number 3, we have observed that on the unit circle, the absolute value of sine and cosine can be represented with the length of a line segment. So if you look at our picture here, and we go back to our other ways we wrote cosine is x over r, and sine over angle is y over r. The horizontal segment, so down here, AC would be cosine theta, and BC would be sine theta. So what's interesting is if now we say tangent of theta, if that's y over x, we have another identity. Just like we studied the Pythagorean identity, another identity is that the tangent of theta equals sine of theta divided by cosine theta. This is another identity that's very important. It comes up a lot. You'll see it next year in pre-calculus. Definitely make sure you write that down and include it in your notes. Okay, so we're going to work through number 4 together. What they've given us here is a similar picture to 3. And there's a line segment in the unit circle. So instead of doing the radius out to AB on the hypotenuse, we can use the radius A to E. And then your hypotenuse goes a little bit past the circumference of your circle. So we want to explain why DE is equivalent to the absolute value of tangent theta. So let's talk about triangle ABC. If we have tangent of theta for that triangle, the opposite side is BC and the adjacent side is AC. So then if we talk about triangle ADE, tangent of theta, the opposite side is DE and the adjacent side is AE. Because ABC and ADE are both right triangles and share angle theta, they are similar by AA. So triangle ABC is similar to triangle ADE. We said by AA, angle, angle. Because they're similar, we can say, therefore, this is a symbol for therefore, tangent of theta equals BC over AC, which is also equal to DE over AE. If both tangent of theta equals these ratios, they're equal to each other. It's a unit circle. So the radius is 1. Let's fill that in. So that means AE is 1. So tangent of theta equals DE over 1, which equals just DE. We did it. It says, explain why the tangent of theta is DE. There we go. So, since our focus is tangent of theta today, we're going to graph it. On the coordinate axis below, we're going to complete the table and plot the points and graph it. I'm going to give myself a little extra room here. We know on the unit circle, let me draw myself a little unit circle, that this point on the radius on the far right is over 1 and up 0. This point 0, 1. Over here is negative 1, 0. And down at the bottom is 0, negative 1. And if you think about our radian measures, 0 radians, pi over 2 radians, pi, 3 pi over 2, and back to 2 pi. We defined tangent as y over x. So starting at 0 radians, y divided by x is 0. At pi over 2, y divided by x, 1 divided by 0 does not exist. So that value is not there. So now let's go to the negatives on my unit circle, on these quadrant angles. Negative pi over 2, remember negative means go clockwise. So this is negative pi over 2. Y over x, that's undefined. Negative pi is in the same location as pi. Negative 3 pi over 2, going to be all the way up here at the positive y-axis, undefined. And then negative pi over 2 is back to the beginning, and that's 0. So now we have these other values in between. For the sake of building our parent graph of tangent theta, you can use a calculator in radian mode to fill in tangent of pi over 8, tangent of pi over 4, and tangent of 3 pi over 8. Oops. So now to graph it, I'm going to draw a vertical asymptote at any value that was undefined. You must draw your vertical asymptotes with a dashed line. And then using these values here, I'm going to plot my points. So let's see, 0, 0. Pi over 4, that's halfway in between, that's 1. And because of the symmetry of the circle, I know negative pi over 4 will also give me negative 1. We're not going to connect the points in a straight line. It's a curved S-shaped piece for each period of the graph. So we can repeat that for in between all the asymptotes. In the middle, you're at 0. Then we have it to the right, positive 1, and to the left, negative 1. On the end here, we're only going to have, oops, I went down too far, sorry, half of a period. This point should have been at negative 1 up here. Do the same thing on my negative pi values. So we're going to pause the video here, and in your groups, see if you can determine all of these key features and properties of the tangent graph now that we've sketched the parent function. Okay, so since the asymptote repeats every pi unit, your period is pi. So if we go from negative pi over 2 to pi over 2, that's a unit of pi. There is no amplitude for a tangent function because there's no maximum and minimum since your graphs approach your asymptotes. The asymptotes, they're all vertical lines, so x equals, we have pi over 2, 3 pi over 2, the next one would be at 5 pi over 2, and so on. So a way to abbreviate that is to say x equals n pi over 2, where n is an integer. So you can also go to the negative side then for your asymptotes. Negative pi over 2, negative 3 pi over 2, negative 5 pi over 2, because integers are positive or negative. Now the x-intercepts we can write the same way. Our x-intercepts happen at every value of pi. You can see it's 0, pi, 2 pi. So our x-intercepts are every n pi, where again, n is an integer. You have to say that part. You have to tell the person who's reading this that your n stands for an integer. And then lastly, for symmetry, it has odd symmetry. If you'd like, later you can look at this website. You can get it off the flip chart that's posted on Edline, but you can look at this website, and it shows you a neat animation of the tangent function being graphed. Okay, there's our properties. Now the remaining class time you can work together on your homework. It's page 41 and 42, numbers 1 through 4.